So thanks for the introduction. Also, thanks again to Cruz. I will try to sketch the optimization problems that we have in Y, so kind of tell you where we need the optimization, and then make like a first draft on how this optimization would look like with the MILP, the mixed integer linear programming formulation. And then also show you where the limits are reached. Good, so the Y project is like a big project with many software loops and packages, and we have 2 points where we need an optimization. The first one is the building sizing, where we make investment decisions. So for example, there we should answer questions like, is it worth adding insulation to the outer walls of a house, or is the profit higher when buying an additional PV panel or when investing in a battery system? So this kind of decisions are kind of optimal solutions which we get by an optimization routine. And the other thing where we need optimization is the control. So we have an energy management system with houses, for example, with PV panels and wind generations and electric vehicles. And then the control has to decide, for example, if the surplus electricity is injected to the grid or if it is used to charge a battery. And it also has to decide, for example, if the electric vehicle is charged during the day or during the night. Good, so I am talking today mainly about the building sizing loop, so about the investment decisions. And I don't talk about the whole system. I will just take out an easy example. So imagine that you have a house and you want to write an optimization routine which tells you if you should buy a PV panel or not, and what size the PV panel should have. So this is kind of an easy example, which I will use to explain the mixed integer linear programming formulation. So the main goal of the optimization is to maximize the profits and minimize the costs in an economic sense. So it's about money. Later on in the Y project, we will also think about CO2 emissions and self-consumption rates and things like that. But the most commonly used example is the economic one. So when you think just about the costs of a PV panel, then you have two terms. You have like one term which is independent of the size of the PV panel, which is, for example, for the installation. So you maybe have to pay a guy who climbs on your roof and installs the thing. And this is independent of the size. And then you have the size-dependent costs, which, of course, 10 PV panels cost more than one. So the installation costs, the size-independent one is called C0, and the other one is the C over P. And P is the capacity you choose for your PV panel, and D is the decision variable, which is 0 if you don't buy a PV panel, and it is 1 if you buy a PV panel. Good, so this is the term which describes your cost, and now I will try to tell you how to convert this term into an objective function. So Cruz already explains that an optimization always has an objective function, which is a function you either want to minimize or maximize, and you have constraints, which kind of are extra rules for your variables. And one limit of the mixed integer linear programming is that we can only consider linear terms. And in the objective function or the cost for the PV panel, we already have a nonlinear term. You see the yellow square where you have the decision variable times the power power of the capacity. And this is a product of two variables, which is not possible in that sense. So in milk formulation, we have to kind of make tricks or apply some tricks. So to get this formula into an objective function, we just get rid of the product. So we cancel the D in front of the P and add an additional constraint. So the constraint is that the power is always less or equal than a maximum capacity. So for example, if you have just 4 square meters of roof, then your capacity is limited and times the decision variable. So if you decide, if your decision variable is 0, you don't have a PV, then also the power is 0 because it has to be less or equal than 0. So this is kind of the way how you linearize problems which are not linear in the first moment. Good, but I would like to come back to the objective function. So if we just consider the cost for the PV panel, then you put that in the optimization, you will always get that you should not buy a PV panel because it costs money. So you also have to think about the profits. And the profits are hidden in a thing which I call running costs. So the profits are hidden in the price for electricity, which you would buy if you don't have a PV panel, and also in the money you get when you inject to the grid. So the injection and the purchase are related to the PV production and the consumption. This is what you see in the figure here, where you have production in orange and consumption in blue, and the resulting purchase and injection in gray and yellow. And a PV panel acts differently during the year, so it will not be the same in the summer as it is in the winter, as it is in the spring. So for the investment decision in the first approach, the easiest thing to do is to consider a whole year. So to get the running costs, we multiply the price for electricity with the purchase at each time step and subtract the injection times the money we get for injecting the electricity at each time step. So we have a sum here over the whole year. And then the objective function, the total objective function, is the investment we saw before plus the running costs. And one thing I should have to say is that the objective function can be less than 0. So here we minimize the objective function, so costs are positive and profits are negative. It could be the other way around. Good, so for the example of the house and the PV panel, I summarized here which variables we have. We have one float variable, which is the peak power. So it describes the size of the PV panel. D is the decision variable, which says, yes, we buy a PV panel, or no, we don't buy it, it's not worth. And purchase and injection are float variables with a size of 35,040. And this is because they have a value at each time step at the year. So if we take a time resolution of 15 minutes, we have 4 time step each hour, then we have 24 hours each day and 65 days a year. And this problem can be solved for a house and the PV panel, but the problem within the Y project is that we do not consider only houses with PV panels, but we have a whole system of technologies. So here you see that we want to include wind, we want to include batteries. We also want to do sector coupling, so we also model the heat demand and heat production. So there's a lot of technologies: heat pumps, heat storages, CHP, hydrogen storages, fuel cells, electrolysis. And when we take this system into consideration, I made a rough estimation of what variables we would have in our optimization. And I mean, this is just the first draft. So we would have about 15 decision variables, which decide if the technology should be included or not. We would have 35 float variables, which give an estimation of the size of the technologies, and 20 vectors of 35,000, which are the energy flows. So for example, if you have a battery, then you have two vectors of size 35,040, where one describes the charge of the battery and the other one describes the discharge. And I mean, technically, this could be all formulated within a MILP, a mixed integer linear programming. The problem is that the time it needs to be solved will be exploding. So we have to do things to simplify the system. And as Cruz said before, the best thing to do is always to decouple things. So we can either decouple in time so that we do not take the whole year, but maybe day after day, or we can also decouple in terms of technologies so that we do not optimize the system as a whole, but maybe just one system with PV and wind and an electric vehicle, and not all of it. And what we will have to do for sure is to do time aggregation. So there are already people who tried or did time aggregation, which just means that you do not consider a whole year, but take out representative days, so that you can reduce the size of this variable by a factor of 10 or 20 or something like that. Yes, and as Cruz explained a lot about genetic algorithms or evolutionary algorithms today, we are also thinking about using genetic or evolutionary algorithms to solve this problem, or at least couple it with linear programming. And yeah, I think that was it from my side. We're really in the first stage, so this is all just ideas and drafts. So I'm really happy about comments in the discussion.